Well, class, today we have Professor Hongsheng Yi. I was recently visiting the department and got to meet him. And his area very exciting, very interesting to me, and I think to many of you will find something new. So he specializes in intelligent robotics and machine learning. And for in my own case, I'm very interested in his knowledge-driven machine intelligence that closes the loop of planning, learning, and doing in-access robotics manipulation and autonomous navigations. This whole area is going through massive progress. Robotics and particularly human-driven or human interactions are extremely important. So, Kaushik, if you want to say hello to Dr. He, you'll be. So I just wanted to make sure Kaushik says hello to you.
Oh, hi Kaushik. How are you?
Good. How are you?
Good, good. Are you all set up? Or move?
No, he still has to do dissertation defense. He did proposal that went very well. Yeah, but he's certainly going to be very ready.
Okay.
By the right time.
That's great.
Okay. All right, we can start. Thank you.
All right.
Go ahead.
All right. Can I start now?
Please.
Okay. Hello everyone. As introduced, my name is Hongsheng He. I'm associate professor in computer science. Thank you so much to Dr. Shis for the invitation, and I'm very glad to share one part of my work. It's about trustworthy human-robot interaction by using natural language. So the idea is using natural language to send instructions and control robots. So this is the topic I'll talk about today. Before we start, I'd like to share a very interesting video about the recent development of robots. This is the figure 1 robot. I hope you can hear the sound.
Hey, figure 1, what do you see right now?
I see a red apple on a plate in the center of the table, a drying rack with cups and a plate, and you standing nearby with your hand on the table.
Great, can I have something to eat?
Sure thing.
Great. Can you explain why you did what you just did while you pick up this trash?
On it. So I gave you the apple because it's the only edible item I could provide you with from the table.
Great. So, based on the scene right now, where do you think the dishes in front of you go next?
Your voice quality is not good, but it can make sense.
The dishes on the table, like that plate and cup, are
Was that really good?
into the drying rack next.
Great.
Well, probably I can explain some. So the human companion is trying to ask some questions and requested the robot to do some tasks for him, and ask the robot to clean up the table and put the object to the right place. The robot thinks is appropriate place for the robot to be placed.
All right, so
And so this is not a recent video, and I think the company has the figure 02. So this is not the name of the figure, but it's actually the name of the robot. It's the figure 1 robot, and I think they are developing the second version, figure 2. So they have integrated ChatGPT. We're working with OpenAI just to put speech-to-speech reasoning into the robot. We know, like, we have the large language models now, we can do a lot of things. They are trying to ground this kind of reasoning process to real robot. That's one trying to show. So just want to show like what you can really do now with the robot by using the current large language models, and how we can use that to improve the interaction. And before we talk about human interaction, so I'd like to introduce the concept of trustworthy. So different people may have different understanding for trustworthy. I don't think we have a common standing for trustworthy. What does it mean for trustworthy communication? What does it mean if you trust a robot or not? So in philosophy, being trustworthy means like having the stable traits and capabilities or capacities that make others justified in placing their trust in you. So from the robotic point of view, that means we can trust a robot because we can predict the actions of the robot and we know what the robot will do. But this is a really funny video I found from YouTube. I cannot justify the source of this video, but just to show what happens. Well, this robot here, probably it was hacked or not. I don't know if it's true or not. But you see, if the robot, even though the robot is really smart, but we don't have trust in the robot because the robot appears too smart. And this can be explained in something in robotics that is called uncanny valley. So the uncanny valley was introduced to represent a particular phenomenon about people liking robots, right? So this shows the design of different robot forms. Like if we have industrial robot, probably we don't like that robot very much. But if it's a humanoid robot, then we increase our likeness for that robot. But there's a part after that robot is designed to be quite similar to our human beings, and there's a big drop in the likeness of that robot. So people will think that robot is scary. And only after we pass that valley, for example, we make a robot that's really, really real and natural, just like human beings, and then we go back to like the robot. So that is the phenomenon called uncanny valley. And I think that we also have the same thing here for the trust in robots. Like if the robot is stable here, then usually we trust the robot because we can program it, we can predict it. But now as the robot becomes more intelligent, maybe for sometimes we lost the trust because the robot is too smart and we cannot control it. That will be the problem. Then we have this uncanny valley in the trust. But eventually we have real smart robots, just like human beings, and we can build the trust with them. So that is the idea, like what we have uncanny valley in trust. So what we are trying to address is the trustworthy human interaction. The idea is, like we all know that the natural language is still preferred for human-robot interaction for all these general settings, just as the video showed. And we really want to develop a way of communicating by using natural language. So we want to control the robot, give instructions to the robot, and we also want to see the robot plan actions accordingly and complete the task. So we believe that to be trustworthy, we need to know what the robot will do, while at the same time, we need to know what the robot will not do. So that is what I mean in trustworthy, and that's what I mean in verifiable actions. And you can see from the video at the very beginning for the figure 2 robot, we see it's really smart and intelligent, and the robot will say what it will do. But what we don't know is, but at the same time, we don't know what the robot will not do. So just give us some instructions, give us some feedback, but we just don't know. We cannot predict the action of the robot. So that is what I'm trying to do. A quick summary of the history about natural language-based human interaction. So like in 1950s, we had the context-free grammar. So simply we use a logical rule to parse natural language and convert that into some kind of understanding for human-robot dialogue. And after that, we have the improved version that is accommodatory categorical grammars. Just introduce semantics into the context-free grammar. And after that, we had different methods based on the CCG, context-free grammar, for robotic applications. Quite a few work there. And after that, we noticed that even though we have the context-free grammar, we don't have logic there. And we introduced a temporal logic into the communication part. Like we can use a temporal logic to give instructions to the robot. It's about 2010. And recently, as the development of LLMs we see a lot of many paper in the field by using LLMs to develop communication with robots. So to go into details with a focus on recent work on LLM-based approach for human-robot interaction, just summarize some work. So the framework is based on syntactics. So once we have the instructions, maybe a paragraph of instructions, by using this kind of grammar, we can parse the instructions into some defined actions. So that is the framework-based framework or the syntactic-based approach. And the language to action is something similar, just match the action verbs in the language, in the instructions, into robot actions. And all the others are recent work using LLMs for planning. So you see, as the name tells, simply what you do is give a really long instruction during the dialogue, and you use large language models to generate instructions, maybe just basic robot actions, or some plans. So this work, GDP PDDL, is one of the interesting work. So I'm going to talk about something similar in this talk. So they use large language models to generate a PDDL problem file directly. So that is usually PDDL later we introduce is a standard form we use for robot planning. So that means they can translate natural language by using LLMs into some kind of high-level implementation, and then you can solve this implementation directly. This is more like translation from natural language to formal language.
Can I ask a question?
Sure.
Yeah. So there is the two pieces of work that I am aware of, not that I'm in any expert in, but Rao, for example, from Arizona State, has argued and shown that LLMs cannot do planning well. And the other part is that your other approaches that you discussed earlier, where you had grammar or logic, there is a lot more deterministic component, while LLM does not have that component. It can, it just does not understand it. It processes the language very well. It generates the language very well, but it does not have endemic understanding of concepts and or what it means in the real world. And that's why people have been working on embodied AI and other things. How are these approaches that you are seeing incorporating the specificity and high, quality of planning support?
Wow, so that is great idea. So that is actually the questions we want to answer here in this talk. So we just proposed a new framework, as you said, to answer these questions. So large language models cannot do planning really well. Do you hear me? Don't hear me well?
No.
Can
We're not hearing you.
Now hear me? Can you hear me now? Still not hear me?
Now we can hear. Yeah.
Okay, great. So I don't know what you hear just now. I totally agree with you. That is really the problem. We know that LLMs cannot generate good plans, and that is the problem I'm trying to address here in this talk. Yeah, so we talk about how we can translate by using LLMs to disambiguate the instructions and how we can map those into semantics while considering the logics. Okay, talk about that. Oh, this is our, like mentioned, this is our framework or story. You see on the left-hand side, this is the instructions and also the instructions. So the instruction introduced to the context, what do we have in the context, how many cups and objects, just like the video showed, like this an apple or something. And the goal is usually some instructions, give instructions to the robot, like just move a cup and manipulate different objects. So what we had in this framework is we introduced this common language. So this common language is kind of a formal language, is readable. It's not just PDDL. PDDL is kind of a script language. It's not really easy to read, and it's not convenient for communication. But what we have here is kind of common language. This one, common language doesn't have ambiguity issues, while at the same time, it can be translated into formal language, just like the PDDL. So by introducing this common language, now we can utilize the capabilities of LLMs in the translation. We know LLMs are really good at general language translation from the natural language instruction to this kind of knowledge. And we'll develop the method to convert this kind of common language into some semantic parts and corresponding scripts. And by using these scripts, we can do verification and decide the problem. And we can also see what the robot is really going to do, because we can see the plan, the sequence of actions the robot is going to take. And once we have this plan, by using a planner, we can have a specific plan defined by robot actions. Like this, we can give semantics to these terms by using perception. Like if you have an object, but use the sensor to associate an object to the term in that plan, and also we're going to associate the action to the action terms in the plan. So that is the idea. We just introduce this common language just to bridge the gap. So we developed this common language. We started from all the grammar inspired by controlled language. So we're gonna have we had a deterministic syntax and the grammar so that we can disambiguate natural language, like improper or ill-posed instructions. We can identify those, and we can disambiguate those. And the other benefits of using this common language is we're gonna have equivalent semantic repetitions. That means we can convert this one into some formal semantics. We can use it for verification and analysis. And there's a big problem is the ambiguity problem and syntax coverage. And based on this kind of grammar-based approach, we have this challenge. Like if we want to cover more, just like we want to have more natural communications, then we need to have a lot of grammar rules. While at the same time, if you have more grammar rules, we can introduce ambiguity. So that is the problem we want to address as well. And so this just shows some scenarios, what we mean by this kind of verification or verifiable actions. Like if we don't have the verification, we simply give instructions to the robot, and robot takes some actions, give some feedback, and the human companion, we just need to observe what the robot will do. But if we have the verification, the robot will feedback with a specific and deterministic action plans, and the human companion will see that before the robot does the job. So that is what they have here in the verifiable actions, and this is what they can do with the common language. So before we talk about the common language, we use the context-free grammar. So remember, this is old school technique, but we found it's very effective actually. So the context-free grammar is defined as a for tuple. We have the finite sets of variables, we have the terminal symbols, and we also have some production rules that is actually the grammar rules. And we have a start with this grammar. So how do we use CFG to parse a sentence? So this is, again, this old topic. So we simply define some lexicons. Oh, somewhere. So we define some actions, lexicons, and then just like some action words, we're gonna parse those actions the robot can do, and we define those. At the same time, we can define some grammar rules. And we can use these rules and the lexicons to parse instructions like this, like pick up the apple on the table, and this is just the parse result. So once we have this grammar parse the tree, and we later do something like semantics analysis or verification. So this is what we did. We developed about like over 300 grammar rules. And surprisingly, we had really good coverage. So this shows all the grammar rules we developed by using CFG, and we observed that about over 80% of the instructions, just natural language instructions, can be parsed by this number of grammar. So I think that's really effective. And we also have dynamic lexicon. So that means we can generate lexicon dynamically from the instructions. Like if we have some description of the problem, and we can directly generate those from the instruction and then construct the parsing process. An interesting issue we had in the common language is the dialects. So that means, as I mentioned, we can only cover about 80% of the instructions. And for that 20%, usually we observe some patterns, just like some patterns that we are not able to parse, like just like units and something like this kind of compound nouns, table leg or something. And we just define a dialog parser or a corrector to correct this so that we can parse it using the grammar. So for this kind of dialect patterns, we didn't define grammar, but we just use some correctors to correct those. So once we have this common language, we want to convert this into semantics. So by using the common language grammar, what we did was we can parse natural language into common language. And we know that common language is free of ambiguity. And at the same time, we know that common language is equivalent to semantics. So we want to convert this common language we just got from the translation part into semantics. We're going to use semantics for plan generation and also for verification. So what we did is, since the common language is a formal language, we just use this ACE parser. So that is a tool that is able to parse formal language into semantics repetitions. So in the work, we use the discourse repetition structure. It looks like this. So this is semantic repetitions of the same instructions and descriptions. And we were able to convert these into actions and descriptions. Later, we will show that we use these two parts differently. So you see, this is the action. If we just have a simple action, please release box 3, and the corresponding repetition in DRS looks like this. This is the predicate, and this is the action, and the action is release, and this is the subject, and this is the object. And similarly, this is the description of the environment, different object, and properties. And once we have the semantics, what we care about most is the action. But for actions, usually we have verbs, and verbs have another issue. That is the polysemy. So that means different words one word could have different meanings. This is just an example of replace. And replace can mean like put something back where it belongs, can mean occupy a position formerly occupied by something else. It could also mean put something in a position formerly occupied by something. So this just showed the example. I adopted this from the lecture by Charles. And you see, this is just an example for this sentence, like John replaced me. You see, this is a single sentence. It could mean different things. So if me is this ball and John replaced me, it could mean John replaced the ball with this rectangle. In this case, if this is the ball, and let me see. Oh, sorry, this is wrong. So if John is the ball, John is the rectangle here. John replace me means the rectangle replace the circle. And John could mean a person, and John simply replace the circle with just another object, a rectangle. And similar here, like if you say like John replaced the telephone, and could means like the John just put the telephone back, or could say like John replaced the telephone with something else. So we have different ways to just interpret the same object the same verb. So that is something we need to address. And then we use the frame net. So frame net is actually a knowledge base of actions. And the idea is like frame net represent words according to the conceptual structures. It's not just the word itself. It's not just like replace, but just like put the word into a context. And that is called a frame. So it's going to be a mental structure of scenarios, not just the object, events, and all associated things. And it contains the frame elements. Those are the things we need to have in the frame. Those are the things that we need to have in the actions. And they also have these lexical units. Is just the action verb itself. That means like we need to know what kind of frames we need to call or execute for that. And this is just an example of the branch for the frame definition of a branch. So like we can see here, because some injuries to something or someone important to an avenger, and the avenger inflicts a punishment on the offender. So the offender is the person responsible for the injury. So this is kind of knowledge about this kind of action. They define this to be an average, a branch, a frame. And this is the list of frame elements. So we need to identify these if you want to use this kind of frame or scenarios. So what we did is, like we have this representation. Remember, we start from natural language instructions. We convert that into common language, and from common language, we have this semantic representation in the RS, and we just represent this into this tree structure. And we design this algorithm to parse this tree just to search for the frames, and we do a frame matching for actions, because we need to generate an action of frames based on the frame. We need to generate the action plan based on this instruction, and this is what we have here. You see, we need just parse different frame elements, and then we can find a good match. So this is going to be a manipulate frame. That means we need to call the manipulate actions we defined for the robot. And those are the elements we need to use when we execute this action. So you can see here, by using this frame, we can have an action template. This is important because we need to have the template to design robot actions. Right? So like for different actions, we need to have different templates. While at the same time, we also have the expert knowledge in this process. Right? So define the actions, and this is the knowledge we can use to execute this action. Just to revisit the idea, we had a natural language, we had a common language, and now we have these frames. And now next part is to convert that into the PDDL plan. So that is a formal language that we can use to define problems, and we can use solver to solve a plan for the robot to execute. I don't know if you're familiar with this one. The PDDL is kind of standard formal language we use in robotics. So it's going to use for expressing planning problems and domains. And it's usually used for automated planning. So we can control an agent by a sequence of actions, and that sequence of actions are obtained by the solver. So why did we use PDDL? We can get many benefits. First thing is we have the expressive expressions and formal representation of the instructions. Now we can clearly see from a high-level point of view what the robot is trying to solve. What is the problem robot is trying to solve? Not up to the level of actions, but from the problem point of view. Is the robot trying to solve a sorting problem on different objects, or is the robot trying to place an object into the plate? Something like that. And we can also handle constraints and resource limitations. Like if we have some constraints, the planner is able to consider those constraints after we define those constraints in the PDDL. And also we have many available planners, really good planners to use. So this is an example of the domain script defined by PDDL, and also the problem scripts. So in in PDDL, we have two types of scripts, just two files. For the domain script, we define the word, like what is in the environment, what is the conditions. You see, in the domain file, usually we define different types of objects. We define predicates, like those are conditions or properties or constraints. For example, if object A is on top of object B, something like that. We also need to define actions. So those actions are defined according to the robot. For a particular robot, we need to define particular actions. So remember, we had frame action frames. So these actions will be defined according to the template of the action frames. So later we can match these actions to the action frames as we required in the instruction. So that is what we have here. So for the actions, we have parameters, preconditions. Precondition means that some conditions that we need to meet before the action can be executed. And the effect defines the results or the consequences of taking those actions. And in the problem script, we just define object and two states. The initial state, this is really high level. For example, we can define like apple, the initial state for the apple is on the table, and the goal state is the apple in the basket. And the solver will figure out, by using the actions we defined here, the right sequence of actions to place the apple into the basket. So that is what we have in the PDL. So this is an example, actually the domain for one of the demos we had. You see, this is the domain file, which is define the predicates, like what is the relation of on, right, small, and properties like green. We also define the actions like move and close, and the parameters needed to perform those actions. And this part shows the instructions we gave to the robots, like just move the red cup on the table with the red hand, something like this, really high-level instructions. And then we just convert these instructions into the problem file that the solver needs to solve. So we just define the goal according to the instruction, and we can generate a sequence of low-level actions to complete this goal. So that is the idea. So we developed the algorithm to parse this into the file, because the goal is to produce the script file. It's a Lisp file. So we need to create every component of that file. So we had developed the algorithm by taking these DRS representations, the semantic representation, and by using these frames, calling the frames, and then we define the goal accordingly. So this is the algorithm. I'm not going to talk about the detail, but just so we were trying to translate this into the goal. And the last problem is the grounding. So we need to ground. Not playing. How do I? Okay, this shows how we ground different actions and perceptions. You see in the semantics, what we have here is some kind of variables like box 3, something defined in the instruction. So we use perception to identify those objects according to the properties. Like if the instruction says pick up the green box on the table, we can use that property, green a box, and trigger the perception action in this plan to recognize the object. And just ground all these variables in this semantic form to the real object in the world, so we can call corresponding actions. So this is some comparison with the recent work based on LLMs. And you can see here, LLM-based method can do really well in parsing the instructions. So they are really good at generating the plan file, PDDLs. So they simply convert all natural language instructions into PDDL. But you can see here the executability is low This is the highest, about 12%. That means the plan they generated are not executable. So that shows a strong hallucination of the RM-based approaches. They can generate the program of the problem scripts, but that is not meaningful. They are not right in semantics. So our approach shows some better performance, even though this is not really big improvement, but we saw that at least for that 1/3 of the instructions we can parse successfully, and we can execute those actions correctly. And we also did, this is a real robot we had in the lab, a dual arm robot with the multi-fingered grippers, and this is just another setup with the projectors just to show the plan. And this is the result, just to show different input. You see the input is kind of complex instructions for different object, different sequence, and we convert this one into these problem definitions, and this is the generated sequence by using the defined robot actions using the solver. This is just the video and demo so that how we do this in the simulation environment. So we just initialize the object at different places randomly, give them properties, and have a paragraph of instructions. And the robot just parse that and figure out now a sequence of low-level actions for the robot to execute like a pick, grasp. So the grounding part, and how do we use the properties to locate and identify different objects. So the variables like position 7 is something we define. Just another example, I believe. Or just randomize the environment so the robot is able to adapt to that. So we don't need to reprogram the robot once the environment has changed. Everything is dynamic. All right. And recently we expand the work to multi-robot settings. We wanted to address two major problems. The first one is the ambiguous natural language instructions. As you can see from the result that the coverage is not really high. We were able to cover about 30%, really complex instructions. And the other thing is we want to consider temporal spatial constraint in the planning problem. So for the first problem, we had this new framework. Previously, we're using the common language grammar to parse instructions. So now we try to use RMMs to do the translation, and RMs are really good at this translation. And we fine-tuned Llama model for the translation. It was really high in the coverage. And the other problem is the temporal and the spatial constraints in the instructions. And now we use the Allen's temporal interrelations to represent these temporal constraints. Now we can only cover the first three relations. We're trying to cover more, but we can only do now the first three. Like if action X happens before action Y, or after, or action X and Y happens at the same time. So this is the corresponding logic rules we need to define in the PDDL. So for different actions, we need to introduce an auxiliary action in between. So you see on the right-hand side, this is a relation between the time for these two actions. Then we need to define these kind of constraints, like to determine the condition for action X and Y to happen in the sequence. And the other problem is the spatial constraints, like for this multi-robot setting, maybe one robot is taking the position and the other robot cannot take it. So what we did is, like for this kind of constraints, like first order logic constraints, like position constraints on conditions, positions, or the conditions on resources, we can either define those as axioms in the PDDF domain file. That means for some relations we need to meet, and we could also define this kind of relations in the action part of the domain file. So you see here, like if you want to define this kind of constraints when we execute the action for the robot, then usually we need to do this complex search, like for all the robot, for all conditions. We need to make sure that the condition is met. And we also do some experiments. So we generate some instructions for the multi-robot using ChatGPT, complex instructions. We put them into different tabs. And we also do a comparison with RM-based approach. And you see, by using RMMs, we can now have a really high executable rate. See, previously it's about 30%. Now we can get about 60% the coverage for the instructions. So that is really good improvement by using RMMs. And now you see the syntax part is almost 100% now because you're using RMMs. This is just some examples we had in simulation for different samples of the instructions. You see, we just give instruction to different rovers in different sequence. We also specify the place they need to be at a particular time, and this is converted into PDDL problem scripts, and we just solve this by using different actions of the robot. So this is the setup, the real setup in the lab. This is for a project working with NASA. So they are interested in using multi-rovers to do some task that is too challenging for a single robot. And this is a real-world experiment. We just run the same task, and we simply control the robot to do navigation and planning. Some ongoing work, we're trying to address the ill-posed instructions. So for now, the instructions somehow need to define the problem. But like for ill-posed instructions, really high-level instructions like clean up the room, clean up the table, we need to generate some instructions. We observed that RMs are able to do this. And we also want to integrate knowledge in the planning process, not just the FrameNet, but some high-level knowledge about planning. We have some precondition and constraints in the planning part, and that is something we want to incorporate. And also, as mentioned, we're trying to do the large language models for formal language translation. We hope we can do like 100% translation from natural language to formal language. Then we can have almost 100% accurate and verifiable actions. All right, okay, that is all I want to share. Thank you so much.
Okay, that was fantastic. I found it very interesting. And any questions?
So, hi. So in a multi-agent settings or multi-robot settings, having a common language, doesn't that defeat the shouldn't it have separate structure and separate what do you mean by a common language representation in a multi-robot setting? Can you...
The common language is what we introduce as a kind of formal language, but it's also readable for human beings.
Okay.
So it's kind of controlled language that we can read, while that controlled language can be converted into formal representation like semantics. We can also know the true meaning of those sentences. That is what we mean by the common language. So talking about, we're asking about the multi-robot setting. This is the instruction generated by ChatGPT, and we need to convert this one into common language. You see, like this sentence, they want to monitor the air filtration unit at word B in the next phrase and report back to the control center. You see, this is really complex and you have different meanings. And we need to convert this one as we did in here. You see, this is just an example. Complex instructions, we need to convert that into this kind of specific deterministic instructions by using the common language. So this is the common language part. You see, this is very it's deterministic and it's short, so we know which robot is doing what. So that is what we're using for using common language for.
So I asked this because like for example in terms of a robot that you showed here, the context like move means certain thing, but for a drawn move has certain other constraints. So
Right.
so it may mean it has altitude and longitude, like there are other things to consider. So how do you, so does that translate here?
Okay, I got your point. So when we do the translation by using the common language, we didn't address those constraints. So we need to first translate natural language into common language so that we can have a formal representation. And based on that formal representation, we can do some planning and consideration for the constraints. As you mentioned, you have some constraints, and we need to represent those constraints by parsing the semantics part.
Okay.
I hope that answers the question.
Yes, thank you.
Okay, thanks.
Thank you very much. Really appreciate it.
All right, thanks. It's glad to introduce the work. All right, thank you.